Hi, my name is Maddie Matthews and welcome to my Physics 2211 Lab 1 report. This lab report is going to be about constant velocity and motion. First, a brief introduction. The purpose of this lab is to demonstrate the properties of Newton's second law at work in the real world. We are doing so by comparing computational models to real videos of movement. For this lab, we use GlowScript to create the computational models, a software called Tracker to gather data on real-world movement from a video we took, a computer to do the code, a camera to capture our video, and a soda can to act as the thing that's moving in our video. So first, a brief overview of Newton's second law. So Newton's second law is usually written as F equals ma, which stands for force equals mass multiplied by acceleration. So basically, if there's no net force acting on an object, there will be no acceleration. And if there's no acceleration, the velocity of the object should stay constant. So for this experiment, the first step that we took was recording a video of an object rolling at a constant velocity. So the object we chose was a soda can, because it was easy to measure the size of. So the system in this setting would be the soda can, and then everything else would be the surroundings. So we recorded this video with the camera and then uploaded the video into Tracker. And using the software Tracker, we tracked the object and created a graph of the position and velocity. And then from there made a chart. And then using a computer, we did some code in GlowScript and created a computational model of what this movement would look like in an ideal scenario. And then we compared the computational model to the data that we received from Tracker. So right here is an example of the video that we took. And you can see the numbers across the screen indicating the different frames of the video as the soda can rolls across the carpet. So these are the graphs that we received from Tracker. The one on the left is graphing the position of the soda can starting from time equals 0, and you can see the position is relatively constant because it's moving or increasing constant amounts because it is moving at a relatively constant velocity. And then over on the right graph, you can see a graph of the velocity from Tracker. So the velocity does appear to be decreasing a little bit. So next, we created a computational model in GlowScript to show what this data would look like theoretically according to Newton's second law. We ignored friction and air resistance in this scenario because we assumed that they wouldn't be affecting the velocity that much. And we assumed no acceleration and a constant velocity to make this model. So this is the GlowScript code that we used. We used the value of around 0.8 for the velocity because that's what it was around the average velocity in the video. And then we used a rate of 30 because we had about 30 frames in our video. And then over here you can see the graphs that we received from GlowScript. So the position would be ideally increasing at a constant rate across the x-axis, and then the velocity ideally would be staying constant. So on this slide, you can see our experimental versus computational graphs. So on the left, it is the actual position versus the expected position, which you can see is relatively the same. And then in our graph on the right is actual velocity versus expected velocity. And you can see that our actual velocity is relatively close to the expected velocity, but it was a little bit higher at the beginning and then kind of trailed downwards as time went on. So possible sources of error for this could be initial acceleration from pushing on the soda can, since it did seem the velocity was a bit higher at the beginning. It could also be due to friction from the carpet, that the velocity was decreasing over time. And also it could just be due to tracking errors in the tracking software, since we have to manually click the center point of each frame on the object, so it's possible that we made a few errors in doing that. So some questions to wrap up would be, If we analyzed our video data and tracker again and flipped the axes, all it would do is flip the signs on the data, but the numbers would still be the same, so it would be relatively the same graphs. And it is possible to say what forces are being added together to give the zero net force, because the forces acting on the soda can would be the initial push, air resistance, friction, and then a gravitational force down and a normal force up. Thank you for watching.